Okay, so one of the things we did last week in trigonometry, we did a lot about right angle trigonometry. You might remember that we did this word SOHCAHTOA, and it meant sine opposite hypotenuse, cosine adjacent over hypotenuse, tan opposite over adjacent. So this word SOHCAHTOA is a way to remember that. So when you're looking at a right angle triangle and you have a given angle here like this, what is the x and what is the 16? Well, the x is the opposite and the 16 is the adjacent. So that tells me, just looking at this, that tan of pi over 6 is the opposite over the adjacent, x over 16. So the question was to solve for x. This means that x is 16 multiplied by tan pi over 6. Tan of pi over 6, that was an identity that you're supposed to learn. So you're supposed to have learned what sine, cosine, and tan of 0, pi over 6, pi over 4, pi over 3, and pi over 2 all are. And we had other techniques to figure out what sine, cosine, and tan of the angles outside of 0 to 2 pi are. But you want to learn what those ones are. Tan of pi over 6 is 1 over root 3. So the answer to this is 16 over root 3. Yes, root 3 over 3 works as well. So if we multiply above and below by root 3 like that, you can also write it as root 3 over 3. Both work. Yep, so that one just kind of incorporated your right angle trigonometry that we did. You want to be able to spot what the opposite and the adjacent are, and you want to know what tan of pi over 6 is for this question. Okay, so we'll get started with the last bit of the course that you have to know. If you've been reading ahead in the textbook, which I hope you have, you probably saw an awful lot of stuff. I'm not going to get through all that today, so only what I cover today is what's going to be in your course. I'm most likely going to skip the graphing section with period and phase and of the sine and cosine functions and everything. I'm going to skip over that, and I'm probably going to skip the very last section as well, trigonometric equations. We're going to meet kind of small equations soon anyway, but we won't go into the more complicated ones. So I think what we're just going to do here, I'm going to review what we did at the end of the last class, because I think if I remember correctly, it was a bit of a mess because my pen ran out of battery and I had to switch, and we kind of ran out of time because of that. So I'm going to go over that again, how to solve for like cosine of 2 pi over 3 and things like this. I'm going to then talk about what if the angle is the variable instead of, so you might solve, say, what's cosine theta equals root 3 over 2? How do you solve for that? How do you solve for the theta rather than just kind of evaluating cosine of some angle? And I'm also going to do trig identities, and I think that's probably all I'll do for today, because I don't want to pack too much stuff into the last class, so I'm going to cut a bunch of stuff out that would have been going in. So only what we cover today will be on your assignment and on your test next week. And while we do have a class next week, we're here from 10 until 1. I won't be actually teaching anything in this class. We're going to be in here doing your final exam, and it's going to be submitted on Gradescope just like the midterm was. So we will have our class next week, but I won't actually be doing anything new. It'll just be the test. So I'll post an announcement about that during the week, like where you're going to find the PDF of it being here in this call, what the rules are for it and everything. So I'll post an announcement about that during the week. But for now, just know that the last class is a test only. It's not going to be more trigonometry. Other than that, you're going to have an assignment coming out today. I'm going to, based on what I get through, in case there's something that prevents me from, I have the assignment made, but if something prevents me from getting to some topic, then I'll have to remove that question from the assignment. So it won't be posted until I get a chance to review the assignment versus what we do in class today. You'll have a quiz on Friday as well. That'll be your last quiz. And then the final exam is going to be on in class next week, and your assignment is going to be due on Monday night before your test. So the assignment will be good practice for the test. It's going to cover lots of things from, I think, the midterm onwards. So just doing that assignment will be good practice for your final. And just make sure while you're doing your assignment as well, you leave some time to review stuff that came before your midterm. The final will cover a little more heavily on stuff that came after the midterm, but there'll also be a few questions from before the midterm too. So just make sure you leave some time to review the earlier content as well. Reviewing for your quiz on Friday should also kind of help with your assignment and your study for your final too. So lots of stuff to keep you busy on that. Okay, so some of the things that we kind of were a bit rushed on last week because of my pen running out and needing to switch to a different computer with a different screen pen. We got a little bit rushed on evaluating trig expressions. So I'm just going to run through a few more examples of those. Hopefully you remember what they were. You had a little look over them before your quiz anyway. But I'm just going to run through them again. So evaluate, let's say first, let's do cosine of 2 pi over 3. We'll also do sine of 4 pi over 3 and tan of 7 pi over 6. Okay, so let's try to remember how to do these. So I gave you a little technique to do these. It's the full version of it is in the notes, but it's almost never necessary to do it. I'm hoping you read through it and you digest it, but I'm trying to give you the shortcut here, the quick way to do it. So what you're going to do is we're going to say the cosine of 2 pi over 3. And somewhere on your page, if you're solving a problem like this, you want to just have this written out somewhere handy that you can kind of keep an eye on it. If you remember what that means, the A stands for all, the S stands for sine, T stands for tan, and C stands for cosine. And what it means is that in that first quadrant, in quadrant 1, all the trig functions are positive in there. They return a positive value. In the second quadrant where you see S, sine is the only positive trig function. In the third quadrant, tan is the only positive one, meaning that sine and cosine are both negative. And in the fourth quadrant, C, cosine is the only trig function that returns positive output, meaning that sine and tan of angles in that fourth quadrant return a negative number. So our technique is to drop this number here so that we just have cosine of pi over 3, and then decide in this original angle that we're working with, what quadrant is that angle in? Is that in the A quadrant, the S quadrant, the T quadrant, or the C quadrant? Can anybody write in the chat for me if you know what it is? A, S, T, or C? Where is 2 pi over 3? A, S, T, or C? Two pi over 3. Yeah, Jamal and Husna have it. Okay, so let me run over this one more time as well. When I'm trying to figure out what angle they're in, if you're looking at the XY axis here and you're thinking about the angle from the X axis, here's 0 degrees, or it's also 2 pi radians, right? So 0 radians or 2 pi radians. Up here would be pi over 2 radians. Out here would be pi radians, and down here 3 pi over 2. So pi over 2 radians is 90 degrees, pi radians is 180 degrees, 3 pi over 2 radians is 270 degrees, and 0 is the same as 2 pi, it's 360 degrees, a full circle. 2 pi radians is a full circle. So when I'm looking at 2 pi over 3 as my angle that I'm working with, trying to decide where that is, ignore the pi's for a second. Just think of what that fraction is, where that fraction 2 over 3 is. If you ignore the pi's, what I'm kind of looking at here in my head is 0 or 2. I'm looking at a half, I'm looking at 1, I'm looking at 3 over 2 like that. Where does 2/3 fit into all that? Because again, I'm just focusing right now on the the 2 over 3 part here. Where does 2/3 fit into all that? 2/3 is between a half and 1. So it's roughly this way. That there would be 2 pi over 3 radians. So S is the quadrant you want, is the second one. Pi over 3, that would be like 1 over 3, 1/3. 1/3 is smaller than a half. That would be in the first quadrant. Okay, good to hear, Jasmine. Make sure you ask questions if you have them. I love getting questions, so if you're not sure about something, always ask. Okay, so that was the first part. The first part is about deciding where would that angle be. And now we've decided that would be in the S quadrant. So what does it mean that it's in the S quadrant? It means the sine is the only trig function that's positive in there, but we're dealing with cosine, so it's negative. And what is cosine of pi over 3? That's something that we learn. That is negative a half. So cosine of 2 pi over 3 is negative a half. Okay. Okay, what's the next one? Sine of 4 pi over 3. So this is going to be similar. First thing we do is we're going to drop that 4 that's on top. Now, what quadrant is 4 pi over 3 in? A, S, T, or C? Any thoughts, Jasmine? I cut out. I was asking what quadrant do you think 4 pi over 3 is? Evan has it. It would be in T. So 4/3. Again, I'm thinking, thinking about the size of fractions and where they might be. 4 over 3 is about 1.3, right? 1.33333. That's between 1 and 1.5. So 4 over 3 would be down here. No, Stephen, it'd be down in the T quadrant down here. Okay. Now, in this quadrant, if you remember, this is A, S, T, and C. Tan is the only trig function that's positive down there, meaning that sine would be negative down there. And what's sine of pi over 4? It's minus root 2 over 2. That's another one that you want to have learned off. So you want to know what sine, cosine, and tan of pi over 6, pi over 4, pi over 3. You want to know those ones off by heart. And then you're going to use those to get any of the other angles that you might need. Okay. Oh, sorry, sine pi, right, yeah. So the very first step was to drop that 4, and then the 4 pi over 3 is where you're looking for. Yeah, pi over 4 would be in the first quadrant, in A. And, okay, last one. And we're going to move on to some kind of harder ones then. So tan of 7 pi over 6. Again, my first step is to drop that 7. And then I have to decide, again, you just kind of want this little drawing somewhere on the side of the page just so you can keep an eye on it. Where is 7 pi over 6? Which quadrant? Maybe this time, Jasmine? I didn't cut out. A, S, T, or C? T, yeah, it's T. So 7 over 6 is between your pi and your 3 pi over 2. 7 over 6, I don't know what exactly that is, but it's just slightly bigger than 1, not as big as 1.5. So that would be in this quadrant. The angle would be somewhere that way. So, and what quadrant is that? That's the T quadrant. Tan is positive in that quadrant, so I don't have a minus sign. It's still tan of 7 pi over 6 is the same as tan of pi over 6. So, I mean, I don't need to write plus there. I can just leave it as tan pi over 6. And what is tan pi over 6? Again, that's something to learn. That's 1 over root 3. Or somebody earlier wrote it as root 3 over 3, which is also correct. Both of those work. So tan of 7 pi over 6 is 1 over root 3. Feeling a little better about those ones? Bit of a refresher from last week. I know it went a bit fast and it was the end of class, so probably a little tired and a little quick for this at the end of class last week. A little refresher there. Any questions about this? I'm going to move on to slightly harder versions of these now. So if anyone's not sure about how to do these, now would be a good time to ask, because it's going to get a little bit trickier. Okay. So to extend this a bit, to look at ones that sometimes get a little bit harder than this, my next question is, what about angles outside of this interval 0 to 2 pi? So we've only dealt with ones that kind of neatly fall into maybe as far as here or maybe as far as here, but into this unit circle here. What about angles that are bigger than 0 to 2 pi? So not just going as far as, 11 pi over 6. What if it's bigger? So for example, what is cosine of, let's say, 11 pi over 3? So 11 pi over 3 is not one of those angles that you would have seen in the unit circle that we did last week. The biggest that the over 3 angles go to was 5 pi over 3, and that was in the 4th quadrant. We haven't seen it get as high as something like 11 pi over 3 yet. So what do we do about that? Well, one simple fact helps here, and it's that adding or subtracting 2 pi from an angle does not change its position on the unit circle. This is probably a fact that you already kind of had in your head anyway. So for example, let's say I have an angle here, and let's say this is theta. What would it be if I added 2 pi to that? Well, here's theta plus 2 pi will be back around to the same angle, right? So adding or subtracting theta, actually I shouldn't write that. Adding or subtracting theta doesn't change the position on the unit circle. They're different angles, but it doesn't change the position on the unit circle. Sorry, I haven't drawn in my unit circle. It won't change the position that your arc is going to on the unit circle. So that means that cosine and sine of theta is the same as cosine or sine of theta plus 2 pi or theta plus 4 pi, theta plus 6 pi, theta minus 8 pi. Any 2 pi multiple, whether you add or subtract, won't change the value of cosine or sine of that angle. So doesn't change the position on the unit circle, and it doesn't change the value of cosine or sine in that way. So back to what we were looking at here. The example was cosine of 11 pi over 3. So what do we want to do here? We want to take this aside for a second and say 11 pi over 3 minus 2 pi. That's going to be 11 pi over 3 minus 6 pi over 3, which is 5 pi over 3. Now, this is something that I recognize. We've dealt with these kind of angles before because they're angles that are inside that unit circle of 0 to 2 pi. So when I see something that I recognize from that unit circle, I stop worrying about taking away 2 pi. So what I can say then is that cosine of 11 pi over 3 is going to be the same as cosine of 5 pi over 3. And I want to evaluate cosine of 5 pi over 3. We've done this a few times already. I'm going to drop that 5 on top. In here, I'm thinking to myself, whereabouts is 5 pi over 3? That's in the C quadrant. Cosine is positive in that quadrant, so I don't need to add a negative sign to correct it. So cosine of 5 pi over 3 is equal to the positive cosine of pi over 3, which is equal to a half. So cosine of 11 pi over 3 is equal to a half. So we're actually able to do this for angles that are outside of the 0 to 2 pi domain as well. Any questions here? You're definitely good with this? Let me get some 1s and 5s in the chat like we used to. Give me a 1 if you have no idea. Give me a 5 if you feel very confident. Thanks, Evan. Everybody else? Okay, very good, very good. 4.3. Okay, good, confident. I'm going to do another couple anyway, just to make sure that everyone's definitely feeling good. So let's do sine of 31 pi over 6. Bigger angle, a little bit more complicated. So I'm going to talk through this one a little bit slowly. Let's say I only have the fact that I can add or subtract 2 pi. So what I might do first is take away 2 pi here, get in the common denominator. This is going to be taken away 12 pi over 6. Oops, sorry, I've used the wrong symbol here. That should be a minus sign. So taking away 2 pi is the same as taking away 12 pi over 6. And what is 31 pi over 6 minus 12 pi over 6? That's 19 pi over 6. So in seeing that, that's not good enough, because I don't recognize 19 pi over 6 as radians that are inside that range of 0 to 2 pi. So I have to do it again. So I'm going to say, okay, 19 pi over 6 minus 2 pi is going to be 19 minus 12 is 7. 7 pi over 6. That's one that kind of rings a bell with me, because I've worked with those already. Those are ones that showed up inside that unit circle that we worked out, and they're angles that I've kind of played with already in practice last week and in class and everything. So 7 pi over 6, I'm thinking that's good. Now, you might be looking at this and saying, that seems kind of inefficient. I did it twice. Why didn't I just do it right the first time? And exactly. So maybe if I was thinking a little bit harder, I could have said to myself, 31 is rather big. So if I just take away 2 pi, it might not be good enough. So what I could have done in the beginning I'll just say that I could have subtracted 4 pi instead of 2 pi twice. Okay. So I could do 31 pi over 6 minus 4 pi. 4 pi, if with a denominator of 6, that would be 24 over 6. Yeah, 6 into 24 is 4. And then 31 minus 24 is 7 pi over 6. And I've gotten there quicker. So that would have been a more efficient way to do it. I'm just pointing out here that it doesn't matter. You can, like if I see 100 pi over something, I can keep taking away 2 pi. It's going to take me a while. Or I could say, I'm just going to take away 20 pi and see what happens that way. So, and if I overshoot it, I can always add some 2 pi multiples back again. So it doesn't have to be perfect. You don't need to come up with some technique to always take away the right amount. You can kind of wing it and say, I'm going to try 20 pi. As long as it's an even number, it has to be a 2 pi multiple. So you can't do like 5 pi or 7 pi. It has to be 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. It's like some even multiple of pi, so that it's a multiple of 2 pi. So what was the question again? It was sine of 31 pi over 6. That's going to be, what we just worked out is that when we took away 2 pi twice, we said that it was 7 pi over 6. We're going to drop the 7 on top, and somewhere we're just going to say, wait a second, I have this CAST thing. Where is 7 pi over 6? That is down in this quadrant down here. Tan is the only trig function that's positive there, meaning that sine must be negative. And sine of pi over 6 is a half, so minus a half is my answer. So sine of 31 pi over 6, we've just worked out, is minus a half. So now we're able to do sine, cosine, and tan of pretty big angles as well, and we can even go negatively as well. So what about one more example here? Let's say we do tan of, let's say we do minus 21 pi over 2. And this one's going to be a bit of a curveball. We haven't done much over 2s. I've been focusing on the over 3s, 4s, and 6s. So let's try an over 2. Okay, first thing I see is that the over 2s that I know from my unit circle are pi over 2 and 3 pi over 2. So 21 pi over 2 is pretty far away from that. So I want to add 2 pi, but I want to add 2 pi a lot to get all the way back to pi over 2 or 3 pi over 2. So can anybody put in the chat if they think, what multiple of pi do I want to add here? This time I'm going to be adding pi because I'm starting with a negative angle. I'd like to make it back to positive. So like in the other ones where I'm doing minus 4 pi or minus 2 pi, this time it's going to be plus 2 pi or plus 4 pi or something. What multiplied by pi do I want to do here? Like 6 pi, 8 pi, 10 pi, 12 pi, 2 pi. Anybody know? You type what it is you think it is in the chat. So I want to take this minus 21 pi over 2 and do plus. So Jamal, the question is, I want to add 2 pi multiple. I want to add a multiple of 2 pi to 21 pi to negative 21 pi over 2, so that I get closer to something I recognize. Like if I go back to my unit circle, the over 2s that I have up here would be pi over 2, and all the way around to here would be 3 pi over 2. So I want to add some 2 pi multiple to get to either pi over 2 or 3 pi over 2, or pretty close. I might not get it right the first time, but I can just add something to get there. So what is the 2 pi multiple that I want to try here? So Evan's instinct, Evan said 6 pi. 6 pi, yeah. So let's see what happens if I add 6 pi. I can do minus 21 pi over 2. 6 pi is the same as 12 pi over 2. If I add 12 to negative 21, I get negative 9 pi over 2. So I'm still not quite there, but I'm closer, so I can just try again. Minus 9 pi over 2 plus, how much do we want to add this time? Oh, Jamal says 11. So I assume he meant starting from the beginning. So you know what? All I was doing there, Evan, really was trying to show that it doesn't matter if I kind of miss the mark. I can just do it again, and I might add 6 pi again, or I might add 10 pi or something. Oh, 11. So we're only going to focus on the even multiples. It's 2 pi is the one. Actually, tan is different. You can actually do pi multiples for tan, but I'm just going to make us stick to even multiples. Okay. So give me an even number if you want me to do it. Or I could continue with the minus 9 pi over 2 and go from there. So Evan, you already gave me 6 pi, so do you want to give me another one to go with? What might I add this time to get closer? 6 pi didn't get me all the way there. I think another 6 pi would work. Jamal, it has to be even. It has to be even multiples of pi. 2 pi, 4 pi, 6 pi, 8 pi. I can't do 5 or 11 or anything like that. So another 6 pi, right? So let's try 6 pi again. See what we get. Minus 9 pi over 2. 6 pi is 12 pi over 2. This gets me to 3 pi over 2. And that's a number that I recognize from my unit circle. So that works. So in the beginning, I could have done 12 pi to get there. But I didn't. I did 6 pi. Not a big deal. I can just go again and try and get even closer. This works. This tells me then that tan of minus 21 pi over 2 is the same as tan of 3 pi over 2. Now that's not one we've seen too much of, but this is where I would kind of go back to sines and cosines. Where's 3 pi over 2? That is down here. That's 3 pi over 2. And what is that coordinate? That's 0, 1, right? So this here, the x coordinate would be your cosine. The y coordinate would be your sine. So sine of 3 pi over 2 divided by cosine of 3 pi over 2, that would be equal to 1 divided by 0, which does not exist. It's undefined. So actually the answer to this question is that tan of minus 21 pi over 2 is not defined. It's kind of a trick one. Okay. So again, we took the same kind of approach of adding 2 pi to get it back into. Why did I add 6 pi to it? Well, 6 pi in the beginning, that was just a suggestion from Evan to say, let's try adding 6 pi to get it back into the correct range. It didn't work immediately, so I added another 6 pi again to make it work. So if I was doing this, trying to do it in as few steps as possible, Stephen, I wouldn't have added 6 pi. What I would have done is added 12 pi in the beginning, because I would say that 12 pi, kind of like on my head, 12 pi is 24 over 2, and 24 minus 21 will give me 3. And 3 pi over 2 is the answer that I want. So this is probably what I would have done if I was trying to do it in as few steps as possible. But it doesn't matter. You know, if somebody misses the mark and they don't get it right the first time, you can always correct it by just doing it again. It was just that the suggestion I got was 6 pi, so I went with it. Why not? It'll still work. This one doesn't exist, and your final answer was that tan of minus 21 pi over 2 does not exist, or is not defined. Any questions here? Do you want to see one more of these before we move on, or are you happy enough? I'm going to wait and see what happens in the chat to see if you want me to do another one, or if you're okay with me moving on. One more. Okay. Lewis, pick sine, cosine, or tan. And do you want it to be over 2, 3, 4, or 6? Pick 2, 3, 4, or 6. Go ahead, Lewis. 4. And pick any number, any big number you want, within reason. Don't pick like 4,930,000,000. Okay. So let's do tan. Do you want positive or negative? Plus or minus? Give me a plus or minus in the chat. Minus. Okay, so let's do tan of minus 33 pi over 4. Okay, my first thought is this is not in my unit circle, so I need to do something. So minus 33 pi over 4. I want to add some multiple of 2 pi. I'm not even sure what it is right now myself. So I guess what I'm thinking in my head here is when I'm adding 2 pi, it's going to be like an 8 pi over 4. So I'm thinking 8, 16, 24, 32. So I'm going to be thinking of some multiple like that. So anybody at all, any thoughts? What do we want to add here? 2 pi, 4 pi, 6 pi, 8 pi, 10 pi? Anybody want to suggest? Eight pi. Let's try 8 pi. So minus 33 pi over 4. 8 is going to be plus 32 pi over 4. That's pretty good. So that gets me to minus pi over 4. Now, some people are comfortable working with negative angles. That's totally fine. I haven't been doing it in this course though, so if you're fine with working with negative angles, you can. If I see it in your assignment or something, as long as it's within, as long as it only goes as far as minus pi, I think I'll accept it. But what I would say for what we've been doing so far is that I'm not quite there yet. 10 pi would have been the right choice. That would have got me to one of the angles that I recognize. So 8 was pretty close, but I think 10 would have been the best choice. But no worries, we can always just take that minus pi over 4 that we got and add 2 pi and see where we go. So minus pi over 4 plus 8 pi over 4 is 7 pi over 4. That is an angle that we recognize from the unit circle. 7 pi over 4 is down here. Cosine is the only trig function that's positive down there, meaning that tan is negative. So just rewinding back a little bit, we had minus 33 pi over 4. That's the same now as tan of 7 pi over 4, which is the same as, okay, we're going to drop that 7, and then we're going to decide, do we apply a minus sign or not? We do, because that's the quadrant, that's the C quadrant where only cosine is positive, meaning the tan is negative. And tan of pi over 4 is one that you're supposed to learn. That's equal to 1. And you get minus 1 as your answer. Now, there's a bit of a cheat. If you learn what sine and cosine are, you automatically know what tan is, because you can just do sine divided by cosine. So if you remember, what you could do is tan of pi over 4, that's the same as sine pi over 4 divided by cosine pi over 4. And both sine pi over 4 and cosine pi over 4, they're both root 2 over 2. So you have root 2 over 2 divided by root 2 over 2, which is equal to 1. So tan, you get the same thing even if you don't learn your tans. But it's probably just better to learn the tans anyway. Okay. Any questions there? Can I see the 1 to 5 in the chat again just for these ones? How do we feel about these questions? Stephen feels good. Evan feels good. Jamal's good. 4s and 5s. 3 for Salome. Okay, most people feel pretty happy. So yes, Salome, if you're struggling with this at all, I see that you're coming in and out of the lecture. I'm assuming you're having some kind of connectivity problem. I think it was happening to you in the academic coaching last week too. So the video, I'll post the video again on online, and you can review it if there's parts that you missed, and you can always send me an email if you want me to talk about any of this if you're not sure. You can see that you're kind of going in and out of the class here. Okay, that pretty much covers our kind of sine, cosine, and tan of those angles. Moving on then to a different style of problem, but kind of not too far away. The next thing I'm going to ask you to think about is, what about problems where the angle is unknown? So far, every time we've solved a problem like this, the angle is given in the question. It's like, what is tan of 7 pi over 4? What is cosine of 2 pi over 3? Or what is sine of 7 pi over 6? And then we figure out, oh, the answer is a half. The answer is root 3 over 2. The answer is 1 or minus 1 or something. So what about, for example, let's say we were trying to solve sine of what? Sine of theta equals negative root 3 over 2. This is a little bit different. This time we're asking, what is the angle that creates minus root 3 over 2? And this can be complicated because you might have seen already that there are at least two angles that work, two different angles. So for example, this one, okay, I'm not going to go into solving it. What I'm going to do is kind of write a bunch of thoughts on this one first, and then I'm going to kind of go back and solve it. So first thing I'll note is that, let's say before starting, note that there's going to be many solutions to this. Many solutions because, first of all, something that we mentioned that we've been using is that if I add or subtract 2 pi from an angle, it doesn't change the value of cosine or sine or tan of that angle. So there's going to be tons of angles that work, infinitely many. Let's say I find out that pi over 3 works. Then pi over 3 plus 2 pi works. Pi over 3 plus 4 pi also works. Pi over 3 plus 6 pi works. Pi over 3 plus 8 pi is going to work. And minus them, and up to 1,000,002, 1,000,004, 1,000,006, 1,000,004. Like all those angles are going to work. If I find a pi over 3 that works, pi over 3 plus any even multiple of pi will also work, or minus. So there's going to be many, many solutions because adding or subtracting 2 pi from an angle does not change from an angle. From an angle theta does not change sine theta or cosine theta or tan theta, but we're dealing with sine in this problem that we're thinking about. So once I find an angle that works theta, adding or subtracting 2 pi doesn't change it. So sine theta is the same as sine theta plus 2 pi. That's the same as sine of theta plus 4 pi, etc. So there's going to be lots and lots of solutions. Before I get to solving it, I think this is one that we actually did earlier. If I go back up here, oh, I have a mistake up here. Yeah, if you notice, I changed, so way back in the beginning, I changed a 3 to a 4 by accident. Did you notice that? So I accidentally changed a number as I was doing it. So my answer here actually should have been sine of pi over 3 is root 3 over 2. So I accidentally changed the denominator going from here to here. I wrote a 4 instead of a 3. So if we did it right earlier, we would have said sine of pi over 3, or sine of 4 pi over 3 is negative root 3 over 2. So all I was really going back to there is that 4 pi over 3 is an answer to this. So I'm going to say recall that sine of 4 pi over 3 is equal to negative root 3 over 2. I haven't told you how to get that 4 pi over 3 yet. All I'm saying is that, okay, notice that 4 pi over 3 works. And also, 5 pi over 3 also works. This is one you can check. You can drop the 5, decide which quadrant, and so on. So the answer to this question would be that all solutions to sine theta equals minus root 3 over 2 are theta equals 4 pi over 3 plus 2 pi times n, and theta equals 5 pi over 3 plus 2 pi times n, where n is an integer. Okay, this would be how you would write your answer. So integers are positive or negative whole numbers. So what this means for the different values of n, for example, let's say n equals 1, 2, 3, 4, 5, I would have 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. If n is 0, I just have 4 pi over 3, which is good because that's one of the solutions. If n is -1, -2, -3, then I'm subtracting 2 pi multiples from 4 pi. Those are also solutions, and they're also true for 5 pi as well. Okay, so just to recap this a little bit, I haven't actually really told you how to solve it yet. I'm still talking through the ideas of the problem and how you might present an answer and so on. So before starting, there's many solutions, because for any solution that you do have, adding or subtracting 2 pi also is a solution. And right now, all I'm saying is, okay, the answers inside the unit circle are 4 pi over 3 and 5 pi over 3. I'm not telling you how I got them yet. I'm just saying those are the answers, because if you evaluate those, you get -√3 over 2. Here's how you would write those. You'd write them as 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n, where n is an integer. Okay. So now I'm going to move on to how to actually solve it. So here, I've given you the idea now. There's lots of different solutions. There's going to be 2 that work in the unit circle, at most 2. And then you're going to say plus 2 pi n for each of those solutions that you get. But how do you actually find those solutions? But how do we find 4 pi over 3 and 5 pi over 3? Okay, so let's start the question from scratch. Here is an example. Let's say it is solve sine of theta equals -√3 over 2. Okay, so step 1 is going to be to drop the minus sign and solve in quadrant 1. So the minus sign that I'm talking about, it's not always there, right? Sometimes you might be solving sine theta equals +√3 over 2. If there is a minus sign, drop it and solve in quadrant 1. So what we're going to do is solve sine of alpha, and I'm using a different Greek letter here, equal to +√3 over 2. So here, what I'm doing is using a different variable, because what I'm really doing right now is I'm kind of solving a different question, but I'm going to use the answer to help me. Now, again, you want to have memorized everything in quadrant 1, sine, cosine, and tan of your pi over 6, pi over 4, and pi over 3. So from your memory, you should be able to say, okay, which one of those gave me √3 over 2? From my memory, what I've memorized in quadrant 1. Well, sine of pi over 3 is √3 over 2. And this here, what I'm calling this is a reference angle. That pi over 3 is going to help me find the real answers. So the reference angle that's going to help me find the real answers. And this is something that should be memorized so far. The answer to sine of what makes √3 over 2, sine of pi over 3 makes √3 over 2. So the first step was to find that reference angle. The next that I'm giving you is that solutions to the question that we want, sine theta equals -√3 over 2, are the corresponding angles to what we found, that pi over 3, in the quadrants where sine is negative. Okay. So Again, I'm going back to this little drawing to figure out what angles what quadrants I'm supposed to be in. What quadrants is sine negative? That is this one here and this one here. So my answers for theta are going to be in quadrants T and C, or quadrants 3 and 4, depending on how you like to think of them. And what are they? So what are the corresponding angles? What are the over 3 angles in quadrants T and C? The ones that correspond to the alpha being pi over 3. So again, I'm thinking, what are the kind of over 3? Somebody joining the class now. So what are the over 3 angles in quadrants 3 and 4? That's what's in my head right now. So when I think of all the angles from 0 to 2 pi, I have pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. These are the ones that we're familiar with. The ones that I want are this one and this one. 4 pi over 3 is in here, and 5 pi over 3 is in there. Those are the answers. So sine theta being equal to minus root 3 over 2. I've made a very long question out of this because I'm explaining every thought in my head, basically. It doesn't always turn out this long. That means that theta is going to be 4 pi over 3, and theta is going to be 5 pi over 3. But don't forget, it's also plus 2 pi n, because we have all those 2 pi multiples of them as well, where n is an integer. Okay? That is how you find them. So running back over this one time, we've kind of made this quite long now, and I've almost forgotten what the question was. So sine theta equals negative root 3 over 2. Your first step is to find the reference angle. If there is a minus sign, drop it and see what the answer would be in the first quadrant. So I'm going to do this. I like to make a new variable because I'm kind of making a new question here. Theta is the angle associated with this number here. I'm going to make a new variable here to find this reference angle. I'm going to call it alpha, and I'm going to use plus root 3 over 2. From my memory, from my work that I've done, I know that sine of pi over 3 is root 3 over 2. So my reference angle is pi over 3. That pi over 3 helps me get to the answers because the question I'm solving is one where sine is negative. Sine is negative in this quadrant and in this quadrant here. What are the over 3 angles in those quadrants? 4 pi over 3 and 5 pi over 3. So those are my answers, plus 2 pi n. Each of them are plus 2 pi n. Okay. Any questions here? Feeling okay? Okay, give me 1s to 5s in the chat again, just so I know how you're doing with this. Very good. We'll do a few more anyway, so don't worry. I'm not going to rush on if you give me too high a mark. 4.22. Okay. 4s. Nobody's quite 100% because they want to see it a few more times. So we will do that. I'm going to do a couple more. So one thing you might be wondering is, what if it's not negative? What if, for example, it's just solve sine theta equals half? So that is one that I'll do where you're not dealing with the negative. So again, I'm going to go through the whole thing of reference angle because even though it's already positive, I like to kind of keep the method the same. Sine alpha equals a half means that alpha is pi over 6. You should have learned that sine of pi over 6 is a half. I then say to myself, where is sine positive? Because a half is not the only answer. It's also going to be somewhere else. It works in here and in here. So pi over 6 is one of my answers. I already have that one. But what is the corresponding over 6 angle in quadrant 2? Well, it's going to be 5 pi over 6. Yes, thanks, Lewis. 5 pi over 6. So all solutions are theta equals pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n, where n is an integer. So that's about how long these questions usually take. I mean, I spent 10 minutes explaining every thought that came into my head for the first one, but they don't need to take that long. So they're, once you get used to them, they're a little bit easier. Yeah. So pi over 6 and 5 pi over 6. And sometimes you're going to see a question like find all solutions to this equation where theta is from 0 to 2 pi. And in cases like that where the question says in the range 0 to 2 pi or whatever, you don't have to worry about the 2 pi n. You could drop it. But when it's just find all the solutions, then you have to think about all the different 2 pi multiples as well. Okay. Okay, let's do another one. So let's say we're doing tan of theta equals minus root 3. Okay. So as always, we're going to start with the reference angle and use that reference angle to help us find the real solutions. So we're going to solve tan of alpha equal to root 3. We drop that minus sign. Again, from all our hard work we do memorizing for the first quadrant, we know that alpha must be pi over 3. I then go to my little diagram. I like to always have this on the side of the page somewhere so that I don't have to picture it in my head. And the more things you put on paper, the more evidence you give me that you're actually doing the work and not using some online calculator or something. I'm going to want to see lots of work in your finals. So where is tan negative? I'm looking at this quadrant here and this quadrant here. So what are the over 3 angles that go in quadrant S and quadrant C? Can anyone give it to me in the chat? It's going to be over 3 anyway. There's going to be a pi on top here. What are the numbers that go up there? Lewis has it 2 and 5. Yep, 2 and 5. That's it exactly. 2 pi over 3 and 5 pi over 3 are the corresponding angles to pi over 3 in quadrants 2 and 4. Very good. Okay. I will do one more, and I think it's hard to get a sense for how people are doing. I'm not being fussy about cameras on in this class because that's a long class and people like to be able to pick their nose without me seeing them. But yeah, it also means that I can't really get a sense for any confused faces and whatnot. So it's always good if you can give me some feedback in the chat. So I'm just going off Lewis, who seems quite quick with this here. And now I'm imagining that everybody is perfect with it and I'm inclined to move faster. So if you want me, if there's a question you want to ask or something, make sure you ask it, because right now all the feedback I see is somebody beating me to the answer. So I'm thinking everybody's great. So make sure to ask any questions if you have them, or I might end up moving a little too quick for you. Okay, so I'll do one more example of it anyway, just for one more for repetition's sake to get used to it. So we're going to solve cosine of theta equals -1/2. Again, we go with the reference angle. Cosine of alpha equals 1/2. In quadrant 1, that would mean that alpha is pi over 3. Okay, so we have another over 3 angle to do. Again, I'm inclined to just put this on the side while I'm doing my work. Where is cosine negative? Yes, so we do have the negative sign here, so we have to look at where cosine is negative. It's negative in these two quadrants here. So what are pi over 3's cousins in quadrants S and quadrants T? Well, it's going to be 2 pi over 3 and 4 pi over 3. So you see how quick we're able to go once we've done a few and once we've done a bit of practice. It went from me talking for 10 minutes and writing all this stuff, and now suddenly we do it in 30 seconds. Now it might be a little longer for you because I suspect a lot of you haven't put in the time learning the quadrant one angles yet. And maybe you haven't done quite as many as I have in the last 15 years or so. So you mightn't be as quick to say, oh, 4 pi over this is in this quadrant and so on. So it might take you a little bit longer, but I'd be kind of expecting people to get these in maybe under a minute and a half if I'm putting it on a test or something. So you might see something like this on a quiz where I would say, you know, what are the angles, and you have to fill in a blank or something, or select the right one from multiple choice, because sometimes that's just the easiest way to ask the question. So yeah, I'd be thinking for this one, something like under 2 minutes anyway to get to solve these. Okay. Tell you what, I'll give you a little break here now. We got through this a little quicker than I anticipated for once. So I'll give you a break here now, and we'll come back at 11:15, and I might be able to take a second break in class. Wowee, look at you. So I'm going to say break until 11:15 a.m. So yeah, if you're going to go get a glass of water or something, I know I am. I'm starting to get hoarse. Just be back in time, and we're gonna move on to trig identities. I'm not going to add more stuff to the course just because we're going a little faster. I'm still only going to cover what I kind of intended to cover today, so don't worry that I'm going a little faster than we expected. Okay, so I'll see you in 10 minutes. If you have any questions, put them in the chat during this break, and I'll get to them when I come back. Hello, everybody. I am back. Take away your break. Okay. So, just get my pen unplugged again. I'm using these breaks to plug in the pen, so hopefully it won't happen again. Are there any questions about anything we've done so far today? Because I'm going to move on to trigonometric identities otherwise. Okay, so everything I'm about to write down here can also be found in the textbook. Let me just skip forward. I'm skipping over the graphs of trig functions, but it's a good little review of graphs of trig functions that I put together. I just don't have time to do it this semester. I'd recommend reading through it, especially if you're thinking of going into physics or engineering or something afterwards. You'll see some of this terminology in probably not in first year stuff, but maybe in second year stuff if you start doing 4-year series and things. You're going to want to be familiar with some of the terminology like the period and the amplitude and the frequency and the phase shift and of trig functions. Just don't have time for it this time, so actually let me share screen here. No. Share. There it is. So yeah, this is not going to be in the course, page 140. I'm not going to ask you about the graphs of trig functions, but I do think that you should have a look at it. It fits into the context of everything we've been doing. It kind of explains how the 2 pi multiples are always the same, and if you edit the function a little bit, if you have like bx, it's not just 2 pi, it's the same anymore. It's going to be 2 pi over b. And so it's interesting, and it's it'll be relevant, especially if you're going into a scientific subject later. But not something I'm going to ask you about, so I'm going to skip on. And we're starting here on trig identities on 6.5. So this is on page 143. Trig identities is what I'm going to do now. So all these things that I'm going to go through, and all these problems I'm going to do, they're all in the book as well. So if it goes a little bit fast, you can always read up on them in the book. And for now, I'm just going to go back to the screen pen. I just prefer to do it on the screen pen. And reshare down here. Okay. So trig identities. Okay, so my first comment is that you already know one. Remember what it is? I've mentioned it a few times. Tan theta is equal to sine theta over cosine theta. That's a trigonometric identity. So what I mean by trig identity is just basically formulas relating trig functions to one another that you can kind of use as a formula in calculations that you might see. So you already have one. Tan is sine over cosine. We met that early enough into our study of trigonometry last week, and we've been talking about it today as well. There's also some new trig functions that you're going to be introduced to now, called the reciprocal trig functions. So the reciprocal identities are the following. So secant theta is 1 over cosine theta. Cosecant theta is 1 over sine theta. And cotan theta is 1 over tan theta. So those are the reciprocal identities. So just to spell this out so that you can see these written. Secant is secant. Cosecant is just secant with co in front. And cotangent is just tangent with co in front. Secant, cosecant, and cotangent. So those are a couple of little formulas you're going to need to learn. You'll see those from time to time in your study of math at university. Secant is just 1 over cosine, cosecant 1 over sine, and cotangent is 1 over tan. This also leads you to one more, right? So cotan theta, just how tan is sine over cosine, since cotan is 1 over tan, then cotan is cosine over sine. Another one. So anything in a box here you should be learning. So I'm just going to maybe put this in brackets. Anything in a box, learn it. I bet there's another trig identity that some of you know, called Pythagorean identities. And they're called Pythagorean because they come from Pythagoras' theorem. So just a little bit of context here. If I draw my unit circle again and think about the first quadrant only for a second, if that's x and that's y, x, it's a unit circle, so it's the side is blank 1. X is cosine theta and y is sine theta. What does Pythagoras' theorem tell you about right angle triangles? It's that the sum of the squares of the two sides is equal to the square of the hypotenuse. So it's going to be that x squared plus y squared equals 1, or cosine squared theta plus sine squared theta is equal to 1. So that's another identity that you have, Pythagorean identity, and it comes from Pythagoras' theorem in the beginning. And there's a couple of other ones that you have with tan and secant and cotan and cosecant and so on that kind of come from that one. So the Pythagorean identities we have sine squared theta plus cosine squared theta is equal to 1. There's also tan squared plus 1 equals secant squared, and 1 plus cotan squared equals cosecant squared. These also need learning. Back up a bit, sure, Maximus. Up there. I'll give you a second to take down whatever you were trying to do. Okay. I'm going to assume you got whatever you're looking for there, Maximus, and I'm going to continue on. So I'm assuming that you've seen these identities before, and this is a bit of a refresher. You've definitely, I'm sure everybody's familiar with sine squared plus cosine squared is 1. Tan squared plus 1 equals secant squared, and 1 plus cotan squared equals cosecant squared. I'm guessing those are, you've also seen them, but for me anyway, when I learned them, I would always mix up where the 1 goes. I might do secant squared plus 1 is tan squared by accident, or cosecant squared plus 1 is cotan squared or something. I kind of mix up which side the 1 goes on. So I'm just going to show you a nice little trick actually to never forget those again. So So I'm just going to say trick to remembering these. Start with the one that I hope everybody knows. Okay, one thing that you can do is divide across by cosine squared, and then you're going to have sine squared divided by cosine squared, cosine squared divided by cosine squared, and 1 divided by cosine squared. Sine over cosine is tan, cosine over cosine is 1, and 1 over cosine, if you remember we just did it, was secant. So that can be how you can remember one of them. And the other one is to divide across by sine squared. So starting with sine squared theta, cosine squared theta, and 1. Sine squared over sine squared, cosine squared, also over sine squared, and 1 over sine squared gives you 1. Cosine over sine is cotan, so cosine squared over sine squared is cotan squared, and 1 over sine was cosecant squared. So it's a nice way to remember. If you just start with the one that I think everybody probably remembers, or I hope everybody, that nobody is inclined to forget this one. Once you remember that one, if for some reason you need to use, say, if for some reason you need to use this identity here, and you're kind of like, ooh, I know there's a formula with tan squared and secant squared, and I don't remember which side the one goes on, or whether it starts with secant squared plus 1 is tan squared or something. Start with the one you know, which I hope is this one here, and divide across by cosine squared, or divide across by sine squared, and see what you get. It's a good way to never forget those identities. Now, there are lots and lots and lots and lots of trig identities. When I was in high school, we used to have a little formula book that they gave us that had log tables. I alluded to log tables the last time, where people will be able to look up logs of certain numbers, and you got all these decimals and stuff. It had all these log tables in it. It had, I want to say, more than 30 trig functions or trig identities like that. There are many, many trig identities that you might eventually need to use. But for this course, I'm really just going through the ones that I've shown you so far that are in the boxes here. And I won't be expecting you to know anything except what's in here to solve any question that I give you. For me, this is really about being introduced to secant, cosecant, and cotangent, and getting comfort with manipulating trig functions and equations, and using the identities to sub them in and out as need be. So I'm not going to be using really complicated trig functions that you might have seen before. Only what you've seen just now will actually be used in calculations that I'm going to go through with you. Okay, so these are the identities that we're going to use, and we're going to do 2 topics here. The first one is going to be simplifying trig identities, so giving you a complicated expression, and you have to use these to kind of simplify it, cancel, and break it down. So you start with an expression and you just make it simpler. And the second topic that we're going to be going through is verifying trig identities. So I will give you an identity, and you have to use the identities on the screen here to see, is that actually true or not? Like, is it true that this equals that, and so on. So first case is going to be an expression, and you work it, you kind of try to make things cancel or add things up nicely. And the second topic is going to be a formula that you have to try and prove if it's true or not. 2 different things we're going to be doing here, and that's actually all I'm going to do with you. I'm not going to go into anything else after that. So, starting with simplifying trig identities. Okay, I'm going to run through this with, sorry, simplifying trig. I shouldn't use the word identities. That's a bad word to use. expressions. I'm not giving you identities just yet. The identities are like formulas in that they have an equal sign, and it's a formula that I'm giving you, and you know, it might be true or it might be not, and you have to either prove it is true or prove it's not true or something. This is just going to be an expression, like a thing full of sines and cosines and tans and secants, cosecants, and you have to try to use the identities that you have to make stuff cancel or to make it into a more clean format. Maybe you factor things, and you know, like you've been doing so far. So let's say your instruction here for this one is to simplify sine theta minus sine theta times cosine squared of theta as much as possible. Okay, so we're going to take this expression and try to think of some stuff to do to it. So when I'm looking at this, I see two possible routes I might take. I'll go through both ways in a second, but anybody in the chat, what is something that comes to mind here that you might do if you were going to try and simplify this? Factor, yeah, Lewis. I might say to myself, I have two terms here. They both have sine theta. So I'm inclined to say, let's factor that sine theta out. And when I do, I'm left at 1 minus cosine squared theta. That's nice. And 1 minus cosine squared. This is a little too hard to ask you to type in the chat, so I think I might just do this one. But I can use a trig identity here. So trig identity applies here. So on the side here for a second, you might remember that you have sine squared plus cosine squared is equal to 1. Well, if I brought that cosine squared across, I would have sine squared equals 1 minus cosine squared. And that is the same as what I have here. And wouldn't it be nicer if I changed that 1 minus cosine squared for sine squared? Because then what I would have is sine theta multiplied by sine squared theta, which is simply sine cubed theta. So that's definitely a more simplified version. We started off with sine theta minus sine theta cosine squared theta, and we just ended up with simply sine cubed theta. That's the kind of thing we're doing here when we're simplifying trig expressions. We're looking at ways we can maybe factor. We're looking at ways a trig identity might apply. Another approach that I might have taken, well, it's kind of the same thing, it's just changing the order, right? So alternatively, so the first thought for this was factor. Lewis looked at this and said, I think if I factor, I see the same thing in two terms, so I'm going to factor, and then the trig identity popped out. Maybe you didn't really notice that, and what you said is, alternatively, suppose we looked at this and we decided to replace the cosine function with sine, because maybe we thought to ourselves, you know what would be more simplified? I could use this identity here to get rid of the cosine and put in sine instead. And then I would have an expression that only has sines in it instead of sines and cosines. That sounds more simplified to me. That's a valid way to approach it. So you might have said this and said, okay, I have sine squared theta plus cosine squared theta equals 1. You might have said to yourself, cosine squared theta, that's the same as 1 minus sine squared theta. So this is something you can do with all these identities I gave you. You can move things around the equal sign and use them as you need to. So you might say, okay, I'm going to replace that with 1 minus sine squared, and then I'll only have sines involved. So this will be sine theta minus sine theta times 1 minus sine squared theta. Now it looks worse right now, but we can multiply out the brackets then. So I can say that this is sine theta times 1, and then sine theta times negative sine squared theta. These are going to cancel, and then we just have sine cubed theta. So we get the same answer. Up here we got sine cubed theta as well. But, you know, somebody might look at this and say, I see two different trig functions in there, but I know that there's a formula between sine and cosine. So I can replace the sine with a cosine, or I can replace the cosine with a sine. I'm going to get all sines in there. And then that to me feels more simplified, because instead of having two trig functions, I have one. But the same thing kind of pops out after you go through the work. Something cancels in the end. Lewis looked at it and thought, I see two terms in there, and both of them have a factor of sine theta. So I can factor out the sine theta. And once you factor it out, you realize that what's left, a trig function also applies here. And you can replace it that way. And you end up with the same thing anyway. So there's often more than one approach, just like in, you know, factoring questions that we did way back in week 1, and I think just week 1 actually, where we might have a different approach to simplify something, but if you do it right, it'll end up in the same place. So that's something to be aware of. Something else that you might see for me, because I see this whole section of simplifying trig expressions all about developing comfort with using them in equations and in expressions, and knowing how they relate to one another and being comfortable with the identities. So something that I might ask you to do in an assignment or in a final or something would be to convert everything to only have sines and cosines, and then simplify as much as you can using only sines and cosines. So convert 1 plus tan theta divided by secant theta to an expression that only contains sine theta and cosine theta. No more tans or secants or cosecants or cotans. Just make it have sines and cosines. And often if you're trying to simplify, that's not a bad approach just to take in your head anyway. Say, because for me anyway, you know, you get used to sines and cosines a lot. They kind of have a meaning on the unit circle where there's angles and they correspond. But when you bring in cotan and cosecant and secant and everything, now they don't really have that kind of meaning anymore. They only really have meaning because they came from sine, cosine, and tan. So for me as well, sometimes I just like to get rid of those ones and bring them back to sines and cosines and back to basics. And that's a good approach too. You can, whenever you're simplifying, you can kind of bring it to sines and cosines and see what happens. So, okay, let's see what we can do here. We have 1 plus, whoops, I'm about to write the wrong question. 1 plus tan theta over secant theta. Okay, what do I see here? Thinking about options. Again, I see two options to begin here. It's probably just about the two possibilities I'm seeing. It's probably just a matter of the first way I'll do this first and this second, and the other option I'll do this thing first and that thing second. Okay, Evan. So here's the problem, right? Let me bring this back to, let's say we had 1 plus y over x. One thing that I can't do, because this is an expression, one thing that I cannot do, let me just remove that because I haven't really got to it. One thing that I can't do with that is just multiply across by x and make it cancel. That kind of operation, yeah, I see. That kind of operation can only work if this is an equation that I'm working with. Something like that, right? Then I can say, oh, I'll multiply both sides of the equation by x to make the thing cancel. But when I'm dealing with an expression, I can't just multiply across by something. It's the same thing when it's sines and cosines and tans and secants. So this is just an expression. It'd be nice just to, so it's always a good instinct to think, I'd like to get rid of denominators because it's always easier to work with numerators only. But it's only possible if what you're doing is an equation, not just an expression. Again, I'd like to ask for your thoughts on this one, but it's kind of hard to type it, isn't it? Multiply the secant to get rid of the division. Yeah, if that worked, that would be easy enough to type it. Which way will I go? Okay, what we could do is just change everything right now. We have these identities. Convert secant, sure. So we can convert secant. We have 1 plus tan theta. Tan theta will also have to be converted soon, but secant is 1 over cosine. Okay. So what do you want to do next? Again, I see two options. I could convert tan and see what happens. I'm feeling like I could multiply above and below the line by something. Or I could kind of think to myself, what happens if I divide a fraction by a fraction? So if I have a fraction in the denominator, there's something I can then do to kind of make that a bit simpler. So I'm seeing a couple of different routes I might go, so I'm wondering what you're thinking. Where would you go next? I'll give you a second to type it out. Feel free to unmute as well if you want. Multiply by, yeah, no, you have the right idea. So whatever means there is if you see, let's get away from trig functions for a second. Let's say I see 1 over 2 divided by 5 over 7. You can change that into 1 over 2 multiplied by 7 over 5. So in this case, the 1 over cosine is going to multiply up into cosine theta over 1. So you're going to multiply by cosine instead of dividing by 1 over cosine. I think that's what you mean. So that's what we're going to do. We have 1 plus tan theta. That's going to multiply by, we flip it and multiply instead. That was one of our rules that we had. So we have 1 multiplied by cosine is cosine. Tan multiplied by cosine is just tan theta, cosine theta. And the original question asked for an expression that contains only sine theta and cosine theta. So let's do something with that. Tan theta. Tan theta is sine theta over cosine theta. So that is just going to be cosine theta plus sine theta. So we started with this expression here that is not very intuitive or something. It's, you have tans and secants and it's division, so it's hard to kind of visualize or see or get any meaning from it. Now it's just cosine theta plus sine theta, so it's definitely in a more simplified form. And there's nothing more I can do with this. You want to make sure you don't make a mistake when you're looking at this and think, we do have a trig identity that says cosine squared theta plus sine squared theta equals 1, but you can't just take the square root of everything here. This is as far as we can go. So we're done. I can't see another way to simplify that anymore, so we're finished. Okay. Let's do another one. We will simplify secant theta divided by cosecant theta times tan theta plus cotan theta. So again, in simplifying, I am inclined to think about things in terms of sines and cosines. Unless you can think of another way to do it. I also see one other possibility, actually. I think that would get complicated before it gets easy. Right here. Yeah, I've seen a lot of options, but I think probably the most straightforward approach would be to turn everything into sines and cosines and see what happens from there. Yeah, we've got 4 different functions in there, so making it just be 2 different functions seems the nicest thing to me. So, okay, we have secant theta divided by cosecant theta times tan theta plus cotan theta. I'd like to let you stop and have a go at this one, but I also have to get to solving trig identities as well, or verifying trig identities as well, so I think I'm going to keep moving. Really have to move so fast this semester. I'd like to be able to stop more and give you a chance to try the problems, and then it gives you a better chance to see where your issues might be and ask questions. We just don't have as much time this semester. Okay, so let's change everything to sines and cosines and see where we go from here. Secant is 1 over cosine. Cosecant is 1 over sine. Tan theta is sine theta over cosine theta. Cotan theta is cosine theta over sine theta. So it looks worse. We've introduced fractions divided by fractions, but for now, at least we just have only 2 different trig functions. So I'm seeing lots of possibilities from where I can go from here, and I might let one of you guys decide which way you want to go from here. So the possibilities I'm seeing are, one thing I could do, so listen carefully to the possibilities I'm going to suggest, and then I'm going to ask you which one you want me to go for. I could sort out these things first and say, okay, 1 over cosine, I can have that cosine without a line, and 1 over sine, that's the same as multiplying by sine. I could put sine on top and cosine on the bottom. That's one way that I could start, is to sort out those 2 kind of complex fractions. I could also, whoops, no, how do I cancel this? I can't. Oh well. I thought I had the highlighter. That was sine and that was cosine. Another thing that I could do is say, okay, I have a fraction minus a fraction inside those brackets. Maybe what I could do is add those and turn them into one fraction, like we did back in week 2 or 3, where we were adding rational expressions. We were getting the common denominator and adding what's on top. That's another approach that I'm wondering if I would take. Another option is I could just multiply this sign into the brackets in here and see what comes out. Addition and subtract. In week 2, yeah, same thing. It's just the minus sign is in the numerator if it's a minus sign instead. So I'm seeing a couple of options. I could sort out what's inside those brackets. I could multiply in the 1 over sine, or I could do the reciprocal things on the outside first. And then I'll probably have to do this stuff eventually anyway, but where would you be thinking if you were going to do it? Oh, it was a oh, thank you. Yes, that was a plus here. I accidentally realized that. Thank you. Okay, where do we want to go? What do we want to do next? Expanding the brackets, why not? Let's see what we get when we do that. So I want to do it your way because whatever the instinct of the student is, I want to tackle it that way and see what happens. So let's multiply the sine in and see what we get. So we're going to multiply this in here and this in here. In that case, we're going to get sine theta over sine theta times cosine theta plus cosine theta over sine squared theta. So what I'm noticing is that sines will cancel here. And now I have 1 over cosine theta on top divided by 1 over cosine theta plus cosine theta over sine squared theta. That might have made it kind of hard. No, we can still go somewhere from here. If we multiply by... Yeah, we can still go somewhere from here. What would be the next step you're thinking about here? Maybe not sure. I think this may have made it a little tougher than it would be if we went a different route. So we could rewind or we could persist. We can still get there if we persist. But Lewis, go ahead.
We can just add the 1 over cos theta plus the other thingy, and eventually it will turn sine squared theta multiplying cos squared theta, and up there it'll be like sine squared theta plus cos squared theta, and that'll be equal to 1, I think.
So I think I missed, what step were you talking about taking?
I mean, we just need to add the things that are down, and eventually...
Oh, you want to add these two brackets, is that it?
Yeah. Yeah.
Okay, and what do you need in order to do that?
Common factor.
Common denominator.
Common denominator, sir.
Yeah. So you want to do sine squared top and bottom on the first one, and cosine top and bottom on that one. Sure. So we can do, Evan, you could also, if you wanted, you could also change that into 1 minus cosine squared. But I think that would be a little tough to continue on with. You would still need to do what Lewis is talking about, where you get the common denominator in order to add them. So that's something that we might do, and then we'd have all cosines. But the denominators will be a little complicated in each of them. That's probably something we're going to do soon. But I'm going to go with Lewis's suggestion here and see what to do next. So what we're going to do is multiply above and below by sine squared, and here above and below by cosine, and see what we get. So we have 1 over cosine theta on top. That one is just kind of staying there for a minute. We have sine squared theta over sine squared theta cosine theta, cosine squared theta over sine squared theta cosine theta. And the whole reason we did that was so that we would have the same denominator, which we do. So we can now combine them. And we're going to have sine squared theta plus cosine squared theta divided by sine squared theta cosine theta. Okay, that was Lewis's step, to combine that into one fraction instead of having two. That's a good step. I'm seeing something quite nice here that we could do. Anyone know what I want to do next? Again, anyone at all, feel free to unmute if you want to just point out something that can be easily simplified here. Go ahead, Lewis.
Sine squared theta plus cos squared theta is 1.
Exactly. This here is a trig identity. That is just equal to 1. That's one of the first trig identities we saw, so we can replace that with a 1. And immediately after that, then I'm going to do what Evan says. We can have them multiply instead of divide. We have a fraction divided by a fraction, so we're going to flip the bottom fraction and multiply instead. Before I do that, I do just want to simplify that because it will involve less writing for me. So 1 over sine squared theta cosine theta. So that's a nice one that we can do that simplified. And now on to Evan's suggestion. This is 1 over cosine theta multiplied by the reciprocal of the denominator instead of dividing. And what we have then is sine squared theta cosine theta divided by cosine theta. And finally, now I think everybody sees you're going to cancel the cosines, and we've simplified this all the way down to just sine squared theta. So we started off with this big nasty function secant theta divided by cosecant multiplied by tan plus cotan. After a whole bunch of work, it all turned down into just simply sine squared theta. So that was a big one, and there was a lot of ways to start it. That's definitely as far as we can go. You could change it to 1 minus cosine squared, but it's the same thing at this point. It's down to just one little trig function. Did anybody else have a different idea at the beginning and you just want to see how it would have worked out? Because this is a big one, and I think there were a couple of options here. For example, would there be a way to do it without changing immediately to all sines and cosines? Probably. There might have been a way to do it. So one other thing that somebody might have thought of would be to look at this first of all and say cotan is just 1 over tan. So I'm going to just go through a different way to do it, just for fun, because this is all just about, you know, seeing a lot of this kind of thing and getting familiar. So I'm going to do it another way, just to see what would have happened. This is all just about developing comfort working with these functions anyway. So all I really want to do today is play with these trig functions. Secant theta divided by cosecant theta times tan theta plus cotan theta. I could imagine that somebody would look at this and say, you know, cotan is just 1 over tan. So one thing that I could do would be get rid of that cotan and write it as 1 over tan theta. Okay? And then you might say to yourself, well, let's try and add those into one fraction and get rid of that, not have that be 2 different things, tan plus 1 over tan. You might say to yourself, that's kind of like tan over 1. So it's the same thing as tan squared over tan. And then you have secant theta divided by cosecant theta multiplied by tan squared plus 1 and my pen is running out again. Unreal. Okay, so I guess I'm going to have to use my my computer instead of the iPad. What I want you to do for the next couple of minutes while I get this sorted is see if you can persist with it in this direction. Tan squared plus 1 divided by tan. And there is a trig identity that looks something like tan squared plus 1. And see, can you apply that and see if there's any different looking cancellation happen than to what I did back above here. So try to continue it this way while I get sorted here with a different way to write on the screen for you. And I will be ready to share screen again in a second, I hope. Okay. Hello. I think I got disconnected somehow. I think my internet went. Can you hear me now? Everyone hear me? Okay, good. My internet just blanked out for a second. Okay, so yeah, the iPad's out of battery, so I'm going to continue on my other screen, which I'll switch to it in a second now. The steps that I had were okay. Looks like I'm having internet problems. Can everyone hear me again? Okay, good. Hopefully this stops happening. Okay, I'm gonna go share my my screen here, and hopefully this won't break again. So this is where we left it. Secant theta divided by cosecant theta multiplied by tan squared plus 1 over tan. There I think I disappeared for a second again. I wonder if it's the call or is it my internet? You all remain in the call whenever this happens? You don't kind of get booted as well, or is it just me? Is it just me that it happens to, or is it everybody? Can you hear me? Okay. It's very frustrating. Let's keep going. Thanks, Devin and Jasmine. So recall from earlier we had tan squared theta plus 1 was secant squared theta. That was one of our Pythagorean identities. So we're going to use that here. And we have secant theta divided by cosecant theta multiplied by that tan squared plus 1 is being replaced by secant squared. And we can make a simplification here. We have, actually, you know what, maybe I'm just going to multiply those brackets first and then make the cancellation. We have secant theta divided by cosecant theta times secant squared theta divided by tan theta. So actually, before we make a cancellation, what I can do as well is treat this as secant divided by 1 multiplied by tan theta over cosecant theta secant squared theta. That's taking the denominator, the fraction in the denominator, and taking the reciprocal and multiplying instead. So then we're going to have secant theta multiplied by tan theta divided by cosecant theta multiplied by secant squared theta. Okay. Secant will cancel with the secant squared here to leave me with just one secant in the denominator. This was something I was thinking about doing over here. I was thinking about cancelling the secant with the secant squared back in this position, but I just thought that it would confuse you a little bit maybe compared to doing it here where it's more clear that I can just do that. And let's rewrite and see what we have. We have tan theta divided by cosecant theta multiplied by secant theta. So I want to try and simplify a little bit further. Maybe it's at this point that we decide to use sines and cosines, because we kind of realize that tan is sine over cosine, secant is 1 over cosine, and cosecant is 1 over sine. So I'm just going to say, recall as well. Why does that happen? I don't like writing on this screen as much as the iPad, so it's a pity the battery ran out again. Recall that we had secant theta is 1 over cosine theta, but that means that 1 over secant is equal to cosine. We also have cosecant theta was equal to 1 over sine. Meaning that 1 over cosecant is equal to sine theta. So when I just go back here and rearrange a little bit, I'm seeing tan theta multiplied by 1 over cosecant theta multiplied by 1 over secant theta. I'm seeing this as tan being sine over cosine, 1 over cosecant being equal to sine theta, and 1 over secant being equal to cosine, cancelling the cosines and ending up with sine squared theta. Now, if you remember, we did it the other way on the iPad, and we got the same answer. We got sine squared, but this time we took a different approach. We started, so I don't have the original question written there, but the original question was, I think it was tan plus cotan inside these brackets here. So we decided we just took a different approach, and we ended up with a very different looking question. This looks very different to the answer that I did earlier, the steps at least, but it ends up as the same thing. So 2 very different approaches lead to the same answer again. That's really all I wanted to show here. Sorry for the interruptions about the internet. I don't know why that's happening. Seems to have stabilized a bit. Hopefully it'll stay stable. Any questions? Okay, so last topic that we're going to cover is, what is happening? Sorry, I don't like writing on this screen as much as the other one, so I'm a little bit worse at it. Last topic that we're covering here is verifying trig identities. Okay, and this is going to look a lot like simplification, except we are given like a formula that we're starting with, and we're trying to do things to it to prove that the formula is true. So we might do some stuff on the left side, we might do some stuff on the right side, and try to show that it amounts to the same thing through a lot of the techniques we've been trying. We've been trying to apply those identities to simplify and cancel and everything. So I think before we start this one, I'm just going to take a short break again. So I'm going to say break until it's 12:11 right now. I'm going to say break until 12:20. And then we'll come back and tackle this last topic, okay? So another quick break so that we're hopefully a bit refreshed and ready to do the last topic of the course. See you in 10 minutes. Okay, let's restart for the last section now. This is really kind of just more of the same, except it's sort of in a different context with an extra little thing to keep in mind. So we won't do too many of these. But I'm going to start with an example of one, and I'm going to get to the... Okay, I think I'm back. Okay, so starting off with another example. Hopefully this stops happening. Sorry about the internet problems here. Hopefully it'll stabilize for the rest of the class. I don't really know what I can do about it. I could probably reboot my router, but that would just make us lose another 5 or 10 minutes, and I think I'm just going to go with it from here. So I'm going to talk through this with an example. And the example is to verify the trig identity below, and it is sine to the power of 4 of theta plus cosine to the power of 4 of theta equals 1 minus 2 cosine squared theta. Okay, so the two tips I have for you, one of them is more of a tip and the other one's more of a rule. But so the tips and rules are these. Before I get into the problem, it's first of all, start with the more complicated looking side. And the second thing is to work on each side separately. So start with the most complicated side and then treat it like an expression, like we've been doing, and simplifying trig expressions from there. Oops, I've written the question wrong. That should have been sine squared minus cosine squared. So start with the more complicated looking side, and ideally you're only going to work on one side and try to turn it into the other one through like the kind of work we did for the last hour or so when we were simplifying expressions. If working on one side alone you can't quite get it into the other side, simplify the left side as much, then simplify the right side as much. At no point should your first step be to write down the equation and then start moving things and multiplying across and stuff, because the first thing that you're starting with in that case is the answer that you're trying to prove. You don't start with the thing you're trying to prove. You start with one side of it and try to manipulate it into the other side, and that proves that the equation is true. Like this thing up here that we are given, this is something that in theory we don't know if it's true. We have to try and prove it. So we start with the left side and try to do manipulations and simplifications and everything to get to the right side. Now this time I said start with the left side because for my first tip it was start with the more complicated looking side. To me, powers of 4 and 2 different trig functions looks more complicated than powers of 2 or whatever. Okay, so let's give this one a shot. So we're going to start with the left side. So the left side is sine to the power of 4 of theta minus cosine to the power of 4 of theta. You know what's coming to my mind is something that we did before earlier in term where we had things that looked like, let's say x to the 4 minus y to the 4. I would be inclined to say that's something that's like x squared squared minus y squared squared like that, and use the difference of squares. So that's what I'm going to do here. I'm going to treat this as sine squared theta squared minus cosine squared theta squared. Okay. Treating this as the difference of squares, what I see then is sine squared theta plus cosine squared theta multiplied by sine squared theta minus cosine squared theta. And the reason I wanted to do that is because, whoops, it's kind of an ugly bracket. This thing in here, that's equal to 1. That's one of our trig identities that we saw earlier. That's equal to 1 times sine squared theta minus cosine squared theta. For a second. There you go, Lewis. You might have missed it. I think I took down the question wrong first. I think I had this here as a plus sign instead of a minus sign, so you might have been just double checking that, I'm guessing. Yeah, I fixed it at some point, but I had written it down wrong in the beginning. Now, it's often at this point that I do like to go up anyway and say, okay, this time I'm not just simplifying kind of aimlessly. I'm looking to make cancellations and use identities. I'm actually trying to get it to something specific. And in this case, I'm looking for this left side here, 1 minus 2 cosine squared theta. So now I'm going to go back and say, okay, I definitely did something helpful there. My instinct was kind of to use the difference of squares and see what I could do. But now I'm down to sine squared theta minus cosine squared theta. But what I would prefer for this question is to only have cosine as my function. I don't want sine in there. Now, luckily, there is a trig identity. Sine squared theta plus cosine squared theta equals 1. I can get rid of sine squared, because I can say that sine squared theta is 1 minus cosine squared theta. And that's what I'm going to do. So I only wanted to have cosines in there. So I get rid of sines using that identity. And now I have 1 minus 2 times cosine squared theta. And again, just double check. That is what I was after in the highlighted blue up there. So I have now verified the identity. So this is how it should look when you do it. You pick a side to start on. Pick either the left side or the right side. And by my first tip, start with the more complicated looking side. If you have something that looks like sine this, cosine that, divided by tan plus secant minus cosecant and all equals 1. What are you going to do with 1? You know what I mean? But if you start with all the complicated stuff, you might be able to use identities, make cancellations and stuff. It's hard to create a whole bunch of stuff out of like something simple. It's easier to get a whole complicated thing and cancel it down to the simple thing. So try to start with the more complicated looking side, which is what we did, and look for something to do. So in my head here, I'm thinking sines and cosines. The identity that comes to my head in this question is sine squared plus cosine squared equals 1. Those powers of 4 look problematic to me because I want to turn them into just one function with a power of 2. So then I remember something that I can do from way back when, back in week 1 or 2, where we're doing difference of squares, and we had a bit of a variation on the difference of squares. Which is what I'm referring to now is what I have written up here. I remembered that we'd seen things like this. We'd used tricks like that to turn that into what this actually works out as when you do it is x squared plus y squared times x squared minus y squared. So we did that with our sines and cosines. And that's a nice way to go because sine squared plus cosine squared equals 1. It's an identity that I'm keeping an eye out for, and it kind of just chops it down nicely for me. I get rid of the powers of 4, and then I can use the identity again to turn it into what I want. Okay, so again, I'd like to know how you're feeling about this. Can I get 1 to 5 in the chat? 1 is this is awful and really hard and confusing, and 5 seems pretty good. I get that. 3.5, 3.8. 4. Anyone else? This is 4 as well. Yeah, it's Just want to see a few more, I guess. So we'll go through another one here. Where am I now? So you can probably expect to see one of these on your assignment and on your final. Not really on the quiz. It's kind of hard to do a verifying identity as a quiz question. So I might struggle to have enough questions. There might only be 4 questions this week because I've cut out some stuff that I was going to do, and some of these questions don't really lend themselves very well to quiz questions, multiple choice kind of. So you might have less questions on it this week. Yeah, this will be in the final, yeah. Just answering Maximus's question there. So verify the trig, probably on the assignment as well. Verify the trig identity cosecant theta divided by cotan theta minus cotan theta divided by, cosecant theta is equal to tan theta sine theta. Okay, so I look at this one, and your first thought that you should think of when trying to solve these is, which side looks more complicated? I'm seeing cosecants and cotans, fractions, a minus sign between the two terms versus just tan theta times sine theta. I'm seeing the left side is much more complicated, so I would start with the left side here. So cosecant theta divided by cotan theta minus cotan theta divided by cosecant theta. Okay, what can I do with this? Any thoughts here? Common denominator, says Lewis. Good, so we'll go for common denominator. So the other option I was thinking in my head was maybe make all sines and cosines, but I like the common denominator approach here. Let's go with that. So what's missing from the denominator on the left term? It's the cosecant. So I'm multiplying by cosecant over cosecant. What's missing from the term on the right denominator? It's the cotan. So I'm multiplying by cotan over cotan. Now, multiplying those out, I'm seeing cosecant squared theta here, cotan theta, cosecant theta, minus cotan squared over here, divided by cosecant theta, cotan theta. Now, the reason we did that is so that there would be a common denominator, the same denominator, and there is now, so we can now combine it. And it's cosecant squared divided by cotan squared, sorry, minus cotan squared, divided by, what am I doing? Divided by cotan theta multiplied by cosecant theta. Okay. What do we do now? If somehow, we always want to keep an eye on what we're trying to do, right? We're hoping that we can turn this into tan theta times sine theta at some point. Now, looking ahead, which is always what you want to be doing here, I'm noticing that cotan is 1 over tan, cosecant is 1 over sine. So that is like tan theta sine theta. So maybe the top should simplify somehow. Maybe the top should be just like 1, because then the whole thing would work out. Is it 1 though? Let's see if we can figure it out. There's a trig identity that relates cosecant and cotan that you might remember from earlier. So let me just maybe use a different color here. I'm going to say, recall the trig identity from earlier. It was 1 plus cotan squared theta is equal to cosecant squared theta. How is that helpful? Well, I could rearrange this. What I'm noticing is what we have on top here, it looks a little bit like that and that. So I'm going to rearrange that trig identity and bring the cotan across. And that looks a lot like that. So I can actually replace that top line with 1. Okay? So I'm seeing 1 over cotan theta cosecant theta. For convenience here, I'm thinking I might just split up those. And again, I want to say recall those identities that we have. We had cotan theta was 1 over tan theta, meaning that with cross multiplication you can then see that 1 over cotan theta would be tan theta. Likewise, cosecant theta was 1 over sine theta, meaning that 1 over cosecant theta is sine theta. So we're going to replace both of those directly. Cotan, 1 over cotan was tan, 1 over cosecant was sine. And that is what we were after. We were trying to show, this is what we were trying to show. We started with the left side here. And we have a whole bunch of equal signs from some simplification and from trig identities. And we got to the right side. So we started with left side and we got to the right side. Okay. Any questions here? So Lewis's idea was to just go for the common denominator and work with the cosecants and cotans. No problem, I'm fine with those trig functions. Somebody else might have said, I'm going to turn everything into sines and cosines and see what I can do from there. So I'm going to say, what if we took a different approach? So for example, let's say we started with, okay, I think I lost connection briefly. Can you all hear me again? I hope. Can you hear me? Okay, good. I saw that little you lost connection thing pop up again, so. Okay, so what if we took a different approach? A lot of people might say, I don't like cosecant and cotan, I want to use sines and cosines and see what happens. Now, I might not go full sine and cosine because I might kind of go sine, cosine, and tan because in the answer that I'm trying to get to, I do want to have a tan in my answer. So I think what some people might do is say cosecant is 1 over sine. And then maybe do some work with the fractions here and say this is 1 over sine theta times 1 over cotan theta. Over here we have cotan theta multiplied by sine theta if you multiply it up. This here, 1 over cotan theta, that's equal to tan theta. Cotan theta is 1 over tan theta. You might then say, I was trying to avoid changing tan into sine and cosine, but it seems hard to avoid. unless maybe we can avoid it. So I can do tan over sine minus sine over tan. Yeah, I can probably do next tan theta divided by sine theta minus sine theta divided by tan theta. Maybe your next step is to get a common denominator, and it's to say, so this is going to be tan squared theta divided by sine theta tan theta minus sine squared theta divided by sine theta tan theta. I don't actually know where this one is going. And again, I'm just playing with the trig functions to see what happens. Tan squared theta minus sine squared theta on top divided by sine theta tan theta. This might turn out longer even. Yeah, I think I do need to change tan to sine over cosine. This would be sine squared theta over cosine squared theta minus sine squared theta divided by sine theta tan theta. One thing I'm seeing that I could do is factor out the sine squared theta. I could then cancel one of the sines on top with a sine here. So I have 1 over cosine squared theta minus 1 divided by tan theta. So divided by tan theta, so again, remember the tan theta is sine theta over cosine theta. So this is 1 over cosine squared theta minus 1 divided by sine theta over cosine theta. So this is 1 over cosine squared theta minus 1 multiplied by cosine theta over sine theta. Multiplying out, I am seeing cosine theta over cosine theta sine theta minus cosine theta over sine theta. That was cosine squared. Way longer than the other one. I shouldn't be using implies here either. So this is 1 over cosine theta sine theta minus, yeah, we're getting there now. So to get the common denominator, I want to multiply above and below by cosine. And we have 1 minus cosine squared theta divided by cosine theta sine theta. So we make that cancellation and we're left with sine theta divided by cosine theta, which is tan theta. That's not what I was after, so I must have done a mistake somewhere. Yeah, this was a way longer way. Sorry for making this more complicated. I forget something along the way, did I? I did. Look, I had a sine theta. that should have been here. So I cancelled only sine theta at the bottom down here. It was supposed to be tan theta times sine theta, as we can see here. So where was that? That was here. So this is multiplied by sine theta. Yeah, this made it harder than it have to be because, so I'm missing a sine theta. What should have happened is a cancellation earlier on, but I lost it at some point. It should have gotten corrected along the way in there. Anyway, point was, that was definitely a harder approach than the original one that we took of just getting the common denominator. But the point is, you can go a different route and still prove it. If you like sines and cosines and just using those two only, you can prove the identities that way. But it's probably best not to avoid them because, as you can see, it was a long, complicated problem if you try to avoid using the other identities sometimes. Whereas if you just kind of face them head on, you can work out a lot quicker. Okay, any questions here? Could do one more with you before we're done here. Let me find one in the textbook. Okay, I'll do one more problem with you. So you can see another one. This is number let's do number 13 in the textbook. So number 13, page 149. Okay. So last one, prove that sine theta plus tan theta divided by 1 plus secant theta is equal to sine theta. Okay. Okay, so I definitely want to start with the left side here. Looks like I picked the tricky one side to help here, to get rid of the denominator. They involve the trig function tan squared or -1, cosecant squared, cotan squared. I would prefer, if I'm going to sort out that denominator, I prefer to see secant squared than secant. I'd also like to, if I can make that squared somehow, that would be a good thing. I'd also like to not introduce just secant on its own. So what I'm actually going to do here is create like that difference of square that we kind of talked about many times in this course. We did it in radicals. We did. Okay. So my internet bugged out for a quick second again, but I think I'm back. Hopefully it can last just another few minutes until the end here. I want to create that difference of squares formula because I know that if I do this, I'll be left with 1 minus secant squared theta, which I can use an identity on. So multiplying this out, I'm going to have theta plus tan theta multiplied by 1 minus secant theta divided by, so you might remember there was a trig function that we had, or trig identity that we had earlier. We had tan squared theta plus 1 equals equals secant squared. So this means that tan squared, and I think that's going to be helpful. So that's something that we can do with the denominator. So we're going to have sine theta plus tan theta multiplied by 1 minus secant theta divided by minus tan squared theta. Next thing I'm going to have sine theta minus sine theta secant theta plus all divided by minus tan squared theta. Looking back at the identity, I want to see sine theta as the final answer. I'm trying to change all those secants and tans into sines and minus. Secant is 1 over cosine, so cosine. And cosine, and secant is 1 over cosine. All this is over negative sine over cosine divided by sorry, my internet really isn't playing ball today. Guess I'll finish it off and hope that we can get to the end then. Okay, so carrying on here then, just reading your question here, Evan. I was wondering, how do you know when to do that difference of squares and when you multiply by that? When you have to do that to both sides. So I'm kind of taking it piece by piece and doing it as an expression. I'm not taking identity and multiplying it. I pick one side of the identity, treat it as this here. That's equal to 1. 1 minus secant theta divided by 1 minus secant theta. Since it's like x over x, it's the same thing divided by itself. I'm putting out again even right now, Lewis. Stephen, you're unmuted. Okay, if I'm cutting in and out, I guess I have to give up. Yeah, but just to go back to all I did really there was multiply an equation. This is like working on an expression. And when you work on an expression, you're allowed to multiply it above and below by 1. If you remember, just going back to radicals. Remember we did this thing if we have like blah blah blah. Whoops. On a highlighter, we might have blah 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 divided by root x plus 1 minus root x minus 1 or something like by the conjugate. It's a little bit like that. The radical things we're working on were radical expression. You're multiplying the expression by 1. If I wanted to just multiply across by the denominator, you have to worry about when it's equal to 1. You don't have to worry about doing it to both sides of an equation. You can do it to an expression. Okay, that question is almost finished. So I'm going to leave it there because the internet keeps crapping out for me. We've done plenty of these now anyway, so what I'll ask you to do is just practice the questions in the textbook and just send me an email if you're having any troubles with anything, and I'll help you in that way. Anything I've done today, I don't know how the video was for the whole class, but hopefully the recording of it is going to be okay, so you should be able to see what I was trying to say at least, because I wonder if the recording is local or if it's recorded through a server somehow. But anything that you've seen, even if the recording was coming in or out, I pretty much follow the textbook, so you can read it in the textbook anyway. And if there's something that you missed because of internet problems or whatever, feel free to send me a message and I can talk you through it in a private meet when hopefully my internet is being a little better behaved. I have really fast internet. I don't know why it's just cutting out today. Maybe it's a weather thing or something. But we've covered more than enough of this anyway for you to get practicing and get doing it yourself. So that is the last class of new content. Next week is the final exam. You're getting an assignment today. I'll be posting it today onto Canvas. If you're someone that's having trouble getting onto Canvas, I know there was some problem with people's participation expiring and stuff like that. If you can't get onto Canvas, just let me know and I can email you a copy of the assignment through email. Hopefully it'll all be fixed and you'll be able to get to the quiz. So assignment coming today, it's going to be due on Monday night, just like assignment 1 was. It was due at like a minute to midnight or something. It was due. Same thing, it'll be due next week at a minute to midnight on Monday. That assignment will be coming out today. You're going to have a quiz on Friday and you have the final exam in class at this time next week, here on this Google Meet call. Cameras on for class, microphones off, and you'll be taking the exam and submitting it to Gradescope. Okay, any questions before we go? Okay, well, I hope you found all this review of the high school math helpful. Yeah, Stephen, we can. When would work? Maybe we can do it right now after this. I'll send you a new link because often there's people that are lingering a little bit. So I'll send you a new link by email immediately after this class. Yeah, I hope you found this review of all your high school math helpful, and good luck in your assignments and quizzes and final and everything coming up. You have a lot of work to do this week. Feel free to send me an email if you're struggling with an assignment question. I can always give a little hint, or if you've made an attempt, which is always preferable, I can say, oh, you made a mistake here, or try this instead or something. So you don't have to do it all on your own. So feel free to send me an email if you're struggling with something. And otherwise, I'll see you in academic coaching if you're with me in an hour. Okay, so take care, everyone. I'm going to meet with Stephen now. I'm going to send you a different link in a second, and I'll just ask you to jump in immediately. Okay. Okay, so take care, everyone, and see you either in an hour if you're with me or next week. Okay. Actually, Stephen, if you're still here, maybe I can just kick people out of this. There's always some.
Yeah, it's fine.
There's always some people that are AFK. Salome, are you here? I'm just going to remove him, actually. This is easier than using a new call.